Yeah, so let's go over these questions one by one. And if you have any of you have any doubts, you can stop me then and there and ask your questions. So the first question is degree of freedom of four link planner manipulator is. So the only thing to notice here is that intuitively it might feel that the answer should be 4, but we are considering the base link also here. So if you just create a manipulator and pardon my bad drawing, I'm getting used to this. So in this, the base link is also counted as the first link. So we have 3 degrees of freedom. That is, we can describe the system using 3 angles: this angle, this angle, and this angle. So this can be as Q1, Q2, and this is Q3. So this is link 1, this is link 2, this is link 3, and this is link 4. So n is 3, and I'm denoting the degree of freedom as n, right? So for question 1, the correct option is 3. Moving on, the second question is also pretty straightforward. Finding joint variables given position and orientation of end effector is known as inverse kinematics. So the other terms here you might also be familiar with. So the opposite of inverse kinematics is forward kinematics, in which we know the joint variables and then we compute the position and orientation of the end effector. The forward dynamics and inverse dynamics are also similarly connected. In forward dynamics, we know the forces and torques and compute the accelerations, while in inverse dynamics, we know the accelerations and we compute the torques or forces that are required to create those accelerations. So the next question is that a vector is given as 1i plus 2j plus 2k, and we have to compute the direction cosines. Okay, so the direction cosines of a vector direction cosines, let's say there is a vector n cap n cap yeah. So let's say there is a vector n given as a I cap plus b j cap plus c k cap. So the direction cosines are given by like a by the magnitude of this vector, that is a square plus b square plus c square, right? So as you can see here, In this case, 1 square plus 2 square plus 2 square will give us 9. Under root 9 is 3. So the direction cosines are 1 by 3, 2 by 3 and 2 by 3. And basically direction cosines give us how this vector is oriented in the 3D space. You can cos inverse of these direction cosines give us the angle that this vector makes with the 3 axes x, y and z. So the next question is based on the concept of homogeneous transformation matrix, which is a 4 cross 4 matrix, and it gives information about rotation as well as translation. So the usual form is this, where R is the rotation matrix, P is the column vector denoting translation, and rest terms, the last row has 3 zeros and a 1. So the inverse, so what is asked here is that you must note it's the inverse of the transpose of the homogeneous transformation matrix. So in the usual case, this is question number 4, I think. Yeah. So in the usual case, if T is a transformation matrix, R yeah, so R P, this is the 3 zeros and we have a 1. So this is a 4 cross 4 matrix, and the inverse of this is given by R inverse minus R inverse P 0 and 1, right? What is asked here is the inverse, transpose inverse, right? So we can flip the order also. We can do first inverse and then transpose also. So T transpose inverse is, I will use this T inverse expression that we have and then transpose it. So first will be R inverse transpose, then it will be minus R inverse P transpose, then there will be 0 and 1, right? So using the formula of transpose, so one thing to note here is that the inverse of the rotation matrix is its transpose. So R inverse transpose will be R itself, because R is an orthogonal matrix. So this will be R. Now the transpose of, so AB whole transpose is B transpose A transpose. So this will be P transpose, minus sign will be there as it is, and again R inverse transpose would be R. Here it will be 0, 3 zeros as a column vector, and 1. So this completes our expression for T transpose inverse, and which belongs to option A. So this is how we can invert the homogeneous transformation matrix. The next question is also based on the same homogeneous transformation matrix. So the 3 cross 3 matrix that we see here, represented by N's, O's and A's. So this is the rotation matrix component of the homogeneous transformation matrix. And as I just mentioned, rotation matrix is an orthogonal matrix. So the columns of an orthogonal matrix are perpendicular to each other. So they form, you can imagine they form a basis of the Euclidean space basically, right? And for any 3 perpendicular vectors, this holds, right? O cross A will be parallel to N, so N dot N will be 1. Let me draw it so that it will be clearer. So question 5, let's say there are 3 perpendicular vectors and we name them as usual, like this is x cap, the x unit vector, this is y, and I guess let's keep this as x so that right hand rotation rule holds. This is y, and then this will be z. So what is being asked here is that x cross y dot z is what, right? So x cross y is z, and z dot z will be 1. So, and this will hold for any rotation matrix because all rotation matrices are orthogonal. So this condition is true, and hence this is the answer for this question, right? Now, okay, so the 6th question reads as follows. F is the fixed frame here, and we are creating 2 more frames, A and B, by a sequence of rotations from F, right? So A is obtained from F by rotation about the z-axis of F by an angle theta, and frame B is obtained again by rotating the A frame about the x-axis of F by angle phi. Right? So let's put down the information that we have till here, right? So let me add a new page. Let me add it here. So question 6, we have frame F and then we are creating frame A. So let's denote frame F and transformation to frame A, right? And this is by rotation about z-axis by an angle theta. So rotation about z-axis by an angle theta. Now frame B, so this is, let's say this is R1. Let's say this is R1. Now frame B, there is one more rotation. So R2, R1, and R2 is rotation matrix about x-axis by angle phi, and the initial rotation was R1, which is rotation about z-axis by theta. So if we write the transformation matrices, so transformation matrix from F to A is R1. Okay, and the second matrix that we know is transformation from F to B, which is R2, R1, right? Now what we are asked in the question is, what is transformation matrix from A to B, right? A to B. So now we will decompose this transformation into this sequence, into the matrices that we know. So first we can write transformation from A to F, transformation from A to F, and then we can write transformation from F to B, right? So we, like this way we can arrive at B from A, and now we have the value of these matrices in before, as we have seen. So now transformation from F to A we know, so transformation from A to F will be inverse of that. So the first part will be R1 inverse into, second is transformation from F to B, which we know as it is, so that will be R2, R1, right? So finally transformation from A to B is given by R1 inverse R2 R1, right? Where R1 is rotation about z by theta, and R2 is rotation about x by an angle phi. So if we compare the options here, this option, you see, this is R1 rotation about z, and this is R2, so R1 inverse R2 into R1. This will give us the transformation from frame A to frame B. So next question also highlights the concepts of rotation matrix and how it transforms points in the space. So there's a triangle in xy plane whose coordinates are given, the coordinates of the vertices, and the triangle is rotated about one of its vertices, which is vertex A. So we want to know what will be the coordinates of the vertices after rotation, and the angle is clockwise 45 degree. So let's come on to this. Question 7. What we have here is there is so a triangle is there, right? 0 0 4 0 and 2 2. So 0 0 is 1 point, 4 0 is 1 point, and 2 2 is 1 point. Right, this is A, this is B, and this is C. Now this is being rotated, right? In rotation we are rotating about z axis, which is perpendicular to this plane, and we keep A fixed, so the axis will pass through the vertex A, right? So the rotation matrix will be rotation about z by an angle theta, and theta is here 45 degree in the clockwise direction. So in clockwise direction we take angle with a minus sign, so minus 45 degree, right? And like figuratively you can think that this will rotate the triangle. I will draw an approximate figure here. So it will look something like this. A will stay there because we are keeping A fixed. The axis is passing through A, right? C will come here, and something like this, it will rotate. So this is to give just a feel of how things are happening in the space geometrically. How to compute it using the rotation matrix? So first we write the expression of the rotation matrix. So since we are working in a 2D rotation, so we can just write the two-dimensional rotation matrix, and since the rotation is about z, so the matrix is cos theta minus sine theta and again cos theta. This is the matrix. Evaluating this matrix at theta is equal to minus 45, this will give us 1 by root 2 minus 1 by root 2, and again there is a minus, so plus minus 1 by root 2 because theta is negative, and cos is again positive. So once we write the rotation matrix like this is the 2 cross 2 matrix, then we can transform the points, and the points are here the 3 vertices. So let's write these 3 vertices as a matrix together. So let's say V is equal to the first coordinate of A vertex 0 0, then B is 4 0, and C is 2 comma 2, so 2 2. So this is a 2 cross 3 matrix. So now we can find the new vertices. V dash is equal to R into V, right? So you can put the values of R and put the values of V and just do matrix multiplication to get the new coordinates. So similarly, this works for any other shape also. So if you will multiply, we can get the coordinates of the rotated triangle. Now the next question is that F is a coordinate frame and M is a coordinate frame whose axes are given in terms of the axis of the F frame, right? So you can see that the ijk of F frame corresponds to some different axis of the M frame. Now the coordinates of point P in frame M is 3, 4, 5. So we need to find the coordinates of point P in the fixed frame, right? So we can do this question in like a couple of ways. Just if you just try to do it directly, we can say that the z coordinate of the M frame becomes the x coordinate of the M frame becomes the negative of the z coordinate in the F frame. So going by that, you can see that if it's 3 in the M frame, then since this is the negative of the z coordinate in the F frame, so the F frame value should be -3. And similarly, the j is just minus sign. So since in M frame it's 4, so in F frame it will be -4, and I will remain as is. So the z coordinate in M frame is 5, which is the corresponds to the x coordinate in F frame. So the point in F frame would be 5 - 4 - 3. And you can do this using rotation matrix also. Like let's say let's start afresh. Okay, so this is question 8. So frame F is given by, we define it as I, j, k, and M frame we define as -k, -j, and I, right? So when when two set of axes are given like this, we can write the rotation matrix of transforming from one set of axis to other set of axis, right? So how we can write is that, so let's denote this ijk as E1 cap, E2 cap, and E3 cap. And similarly, let's denote it as E1 cap prime, E2 cap prime, E3 cap prime. Okay, so the rotation matrix of transformation, so its elements you can write using this approach. So it will be E1 prime dot E1. Second will be E1 prime E2. Third, E1 prime E3. So what this dot product is giving, basically it's giving the cosine of the angle between these two vectors basically. That's what dot product gives us between two unit vectors. So we are writing cosine of angles between these two unit vectors. And again, the next row would be E2 prime E2 sorry yeah, next would be E1 prime this will be E2 prime dot E2 and this will be E2 prime dot E3 and the last row would be E3 prime dot E1 E3 prime dot E2 and E3 prime dot E3. Cool. Now we have the values of E1, E2, E3 and E1 prime, E2 prime, E3 prime, right? So what we can do, oh wait, I think this got erased. This is F. So let's just quickly compute these dot products. So E1 prime E1 would be I dot k. So these are perpendicular vectors. So this would be 0. Again E1 prime dot E2. Again it is perpendicular. So 0. And E1 prime E3 gives k dot k with a minus sign. So -1. So next would be E2 prime, which is minus j. Again the first term would be 0. This would be -1 and this would be E2 prime j dot k, again perpendicular, so 0. Third row E3 prime I cap I dot I1, this will be 0 and 0. So this completes our rotation matrix. Right, and now what the point that we had was in express the coordinates of point P in M frame. So coordinates of point P in M frame is given by 3, 4, 5 and we need to find coordinates of P in F frame, right? So now this rotation matrix that we have computed, this transforms from M frame to F frame, right? So we can write M frame to, my bad, wait, three, four, five, right? So now if we multiply the rotation matrix, wait, I will rewrite this. So this rotation matrix transforms from F frame to M frame, right? And we have to go from M to F frame. So what we will do, we will multiply the coordinates of in M frame with the inverse of this rotation matrix, right? So F P is R F M inverse M P, right? Now inverse of rotation matrix is its transpose. So let's transpose this matrix. This will be 0, 0, 1, 0, minus 1, 0, and minus 1, 0, 0. And what's the coordinates in M frame? They are 3, 4, 5. So now we have to just do the matrix multiplication, which will give us another 3 cross 1 vector. So this will be 5 minus 4 and minus 3, right? So we are getting the same value as we computed just by intuition. So this could be the proper way of doing it. What we do, we have the vectors defining the axis of both the frames. We write the rotation matrix transforming between the two frames by computing the dot products between every pair of these axes, and then appropriately we multiply with the forward or the inverse transformation to transform from one frame to another frame. So question 9 says that R is a rotation matrix and R dash is its transpose. Is there any question? Good. So R dash is the transpose and P is a column vector. And this is the same homogeneous transformation matrix, and the result is also pretty straightforward. We know that R is an orthogonal matrix, so RR transpose will be identity matrix. And finally, there's a 3 cross 3 rotation matrix given. there is a 3 cross 3 rotation matrix given, and we have to tell this corresponds to which rotation. So since the first entry is 1, so that tells us that this rotation is about x-axis. And if we compare the expression of rotation about x-axis, which I will write here, so question 10, rotation about x-axis by an angle theta is given by, since we are rotating about x, this will remain the same, and other are given by cos theta minus sin theta, sin theta and cos theta. So if we compare from this, we can see that cos theta is root 3 by 2, or sin theta is minus sin theta is half, right? So this will give us the information about the sign or the direction of the rotation also. Minus sin theta is half, so theta should be minus pi by 6, my mistake. So theta should be minus pi by 6. So this is a rotation. What does the minus sign denote? It denotes that the rotation is in clockwise direction about x-axis, right? So this covers up the first assignment. Let me quickly move to the next assignment. Any questions till here? You can ask. Okay. So this assignment mostly covers the concept of DH parameters, which is used to assign frames in robotic systems and basically write transformation matrices. So it lays out a systematic procedure while writing transformation matrices for these systems, so which can get sometimes bit complicated and tedious also. So this helps in developing a standard procedure for these systems. So before we start, we can quickly go through the DH parameters. So the symbols, I guess, more or less you would be familiar with. ZIs denote the lines along the degree of freedom of the. So ZIs denote the axis of rotation or the axis of translation in case of prismatic joints, right? So for revolute joints, it would be perpendicular to the plane of the motion, and for the prismatic joints it would be along the line of motion. So those are ZIs, and XIs are the common normal to the ZIs basically. So let me see if I can pull up a picture quickly. So yeah, so it would take me a lot of time to draw this, so I'm just referring this diagram here, right? So as I was saying, ZIs are the, in case of revolute joints, they are the axis of rotation, and for prismatic joints they are along the direction of motion. XI is the common normal between two ZIs. So let's say this is this blue one is one ZI minus 1, and another is ZI, and XI minus 1 is the common normal of these two vectors basically. So with this information only we can solve the first question, which says which one is of this is true. So zi cross zi minus 1 will give us a vector perpendicular to both these vectors, and as I mentioned, xi is a common normal, which means xi is perpendicular to both zi and zi minus 1. So xi is parallel to a vector perpendicular to both these zi and zi minus 1. So this statement is true for frames defined by TH procedure. Now again, let's move ahead in this diagram. So we have four parameters here. Theta I is the joint angle, which is basically the angle between xi minus 1 and xi, right, along about zi minus 1. So theta is called the joint angle. Di is the joint distance. It is the distance between the origin and the point where the common normal intersects the zi minus 1 basically. So xi minus 1 and xi and zi minus 1 intersect here, and the distance between these 2 points is di, which is joint distance. Now ai is the link length parameter. So this is the distance between the these two intersection points basically, what it is said as, I guess, bi. Yeah, so it is distance between bi to oi. This is ai. And finally we have the twist angle alpha I, which is the angle between zi minus 1 and zi about xi. So what is asked here is that basically it's the definition of joint distance. So joint distance di, as I mentioned, is the distance between oi minus 1 and bi. So this is oi minus 1, like the origin of this joint, and this is bi. So this is di, the joint distance. The next question is again, so we have the Jacobian matrix and it's a 3-link manipulator. We have q dot. What it is the joint velocity. Basically it's the rate of change of the 3 angles. And why there are 3 angles? Because it's a 3-link manipulator, so it's described by 3 angles. And we have to compute what's the velocity of the end effector at this instant, right? So this is a 6 cross 3 matrix, and we have here 3 cross 1 matrix, right? So the end effector's velocity is given by jq dot. So let me save this document. And I will okay, so yeah, so we are on question 3. So question 3, what's given is the Jacobian. So basically Jacobian matrix, what it does, it relates the angles and the position of the end effector basically, right? So in a sense you can say that you can do forward kinematics using Jacobian matrix. So let's say let's say there is a Jacobian matrix with some entries A, B, C, D, right? So what this will do, let's say we know for this example, like I am deviating a bit, let's consider a 2R manipulator, right? So this is theta 1, this is theta 2, right? So let's say we know theta 1 and theta 2. So generally Q is used to denote the quantities in joint space. So Q is the vector of joint angles theta 1 and theta 2, and if we want to know the position of the end effector, this is the end effector, so let's say P. So position of P you can find by multiplying the Jacobian with the joint angles. So JQ, right? JQ gives the position. And similarly, the velocity of the end effector is given by JQ dot. So we have the Jacobian here. And let's say if we multiply it to this is 6x3 matrix, this is a 3x1 matrix, and if you multiply you can see that this you can get this result. So 300 into, you will finally get this answer on multiplying J and Q dot. So JQ dot gives the velocity of the end effector. Now the fourth question is a little bit longer, so let me first cover the other questions and then I will come back to this, right? So question 5 says, if a point P, X, Y, Z in coordinate frame rotates about the Y-axis with angular velocity 0.02 radian per second, then we have to say what's X dot and Z dot basically. So you can imagine it here that question 5. So question 5 so this is the coordinate frame and we have Y here, X here, Y here, and Z here, right? So what it's given is there is a point here P, X, Y, Z, right? And the point P is rotating about y-axis, right? So point P is rotating about y-axis. So point, yeah, is rotating about y-axis. So we know that if a point, let's say this is an axis, and if a point is rotating about this axis, right, let's say r, and this is omega, right? So the velocity is given by omega cross r, right? So basically what we do, we multiply the perpendicular distance of this point P from this axis into omega, right? So omega is here about y-axis, right? And it's given 0.02 radian per second. So 0.02, and the direction will be j cap radian per second, right? And r is r in the coordinate frame is x I cap plus y j cap plus z k cap, right? So what we have to do, we have to compute the cross product between these two vectors. So velocity is omega cross r. So since we can do the cross product here, so it will be 0.02 x j cross I, j cross j would be 0, and the other component would be 0.02 z j cross k. So this will be 0.02 x, and j cross I is minus k, plus 0.02 z, and j cross k is I, right? So this will be 0.02 z I cap minus 0.02 x k cap, right? So what we have been asked, we have been saying what's the x dot is basically velocity in x direction, z dot is velocity in z direction. So x dot is 0.02 z, and z dot is minus 0.02 x. So this is x dot, and this is z dot. Yeah. So again, using basic concepts of cross multiplication and the relation between angular velocity and linear velocity, we can get the result. Just give me a minute. Yeah, so the next question is, we have a sequence of transformations, and so all these are homogeneous transformation matrices, and the notation, as you are familiar, is that this matrix transforms from 0 to 1 and is expressed in the 0th frame. This is from 1 to 2 expressed in the first frame, and so on. So what we have been asked is to find the homogeneous transformation matrix 0 to A, not A, I think, yeah, 0 to 4, yeah, this is the correct one. So how we can get transformation from 0 to 4 when we have the matrix of the transformation for each step? So basically we have to multiply it. So this is question 6. Yeah. So question 6, we have to find transformation from 0 to 4. So this will be transformation from 0 to 1, then 1 to 2, then 2 to 3, right, and then 3 to 4. So we can do this set of matrix multiplications, so and then we can get the final transformation matrix. So this problem is pretty much straightforward. We have to just multiply these 4 matrices and put the values of theta 1, q2, q3 and theta 4, and we will get the final result. So yeah, this is this is how we can get transformation from the 0th frame to 4th frame. And again, this question is also based on the previous question itself. So delta t by delta theta 4 is basically you will get an expression of t in terms of these quantities, theta 4 and theta 1 and q2 and q3. So we can differentiate that matrix with respect to, partially differentiate that matrix with respect to theta 4, right, and then again evaluate that matrix using these given values, and we will get this answer. Now the next question, the next question is in 6 the third column of Jacobian for mentioned values. So again, Jacobian also we can get when we compute this transformation matrix. Now coming on to the 9th question, So we have a system here which has like rotation about this axis, then there is a rotation about the EF axis, and we have been given these dimensions OA, BC, DE, and EF, right? So we have to compute the homogeneous transformation matrix 0 to A. So the approach in questions like these is to first identify the links, the joints, and then assign frames according to DH parameters. Find the DH parameter table, and then use the the transformation matrix computation formula to compute the transformation matrix. So let's come on to now. So generally, like the other two questions are also based on DH parameters itself. So let's revise DH parameters once. So DH parameters. So as I mentioned, DH parameters are a set of 4 parameters that we assign, like DI, theta I, alpha I, and AI, right? So DI is the joint distance, theta I is the joint angle, alpha I is the twist angle, and AI is the link length parameter. Link length, right? Now let's say we want to write the transformation matrix of the ith matrix from the I minus 1th matrix. So we are transforming to the ith matrix, sorry, to the ith frame from the I minus 1th frame. Now this is given by this, you would be familiar with. So the sequence basically is reverse of what I'm writing, so things are getting pre-multiplied basically. So there, first I will write and then I will explain. Zi minus 1 theta I translation xi and rotation. xi alpha I. So the sequence is basically starting like this. First we rotate about xi by an angle alpha I, then we translate along xi by a distance ai, then again we rotate about zi minus 1 by angle theta I, and then translate zi minus 1 by distance di. So if we write the transformations for each of these four transformations and then multiply, then we get the final transformation matrix, which is used to directly compute the transformations from one frame to another in these systems. So let me again write it. This is cos theta I. So c theta I will usually use to represent cos theta I, and s theta I will be sin theta I. So just to make things less cluttered, c theta I minus c alpha I sin theta I sin alpha sin theta I. Do check these expressions, like, to see if these are correct, because it's very easy to make mistakes in these. So next is s theta I c alpha I c theta I minus sin alpha I c theta I ai sin theta I. Then there is 0 sin alpha I cos alpha I and di, and the final row is 0 0 0 1, right? Okay, so yeah, so this is how we can, and once we know the values of theta I, alpha I, di and ai, then we can compute this matrix, and for that purpose only we create what is known as the DH table basically. So now let's copy this diagram from here and let's try to compute the DH table. So basically this O is the fixed part and F is the end effector, right? Here theta 1, so one revolute joint, again theta 2, it rotates about this, so second revolute joint, and theta 4 is the third revolute joint, and I think, okay, so let me start the table. So we have the joints are 1 2 3 and a 4, and we have the TIs, the AIs, right, the alpha i's and the theta i's. Okay, so now coming to the first joint. So what was di? Di was the joint distance, basically distance from origin of the I minus 1th frame to the bi point along zi minus 1, right? So this figure, so basically the first, since the directional rotation is like this, so you can imagine that the zi will be also along this only, OA, right? And and the distance between O and this point will be d1. So this will be d1, right? Then we zoom it out. Yeah, d1, and then we have a1, a2, and d3, d4. Okay, so now the AI AI is the link length parameter. So for the first case, this will be a1 itself, right? Twist angle is 0, and since rotation is theta 1, so we will be writing theta 1, right? Rotation is, yeah, here, so theta 1. Okay. Now theta 2 rotation is in the negative direction. Since we are theta, we measure about the zi minus 1, right? So zi minus 1 is from O to A, upward you can say, and theta 2 is rotating in the negative direction of that. So theta 2 will be minus theta 2, right? Alpha I is again 0. Alpha I, as you remember, is the angle between xi's, and xi's are, yeah, alpha I is the angle between, sorry, zi is about xi, and zi are parallel here in the opposite direction but parallel, right? And the, wait, let me draw a line here. Okay, now the link length parameter will be a2. Okay, and d is the distance between, again, distance between the origin and the point where xi and zi intersect, basically. So the zi is in this direction, right? And common normal is in this direction. So the intersection point and origin point, they are both here. So this distance is 0. Now coming on to third joint. So third we have D3, right? So the angle first theta, so there is no theta angle here, so this is 0. Twist angle is the angle between zi's about xi. So again, this zi is upward, this is downward, so there is a 180-degree twist. So this is 180. Now the link length basically, so link length is distance between bi and oi. So in this case yeah, in this case the origin and the intersection point both lie at C, so this will be 0. And finally we have the D3 parameter. So D is measured and finally we have the fourth one is the end effector, right? So end effector is just rotating and everything else is along the previous axis only. So D will be 0, this is also 0, twist is also 0, and this is theta 4, right? So now that all these parameter values we have, so one by one we can compute T01, T12, and similarly like in the previous question we did. So T4 from 0 is basically T4 from 3, T3 from 1, sorry 2, T2 1, and T1 0. So one by one we computed DH table. We know the expression of the matrix of transformation between the two frames. We put the values of DH parameters one by one, compute these matrices, and then multiply them to get the final transformation matrix, right? So this is how we proceed on questions like this. So I will leave the like similar questions you might have in your assignments also of this time, and you can proceed on these lines to solve the questions based on DH parameters. Right, so any doubts in these concepts or any other questions in general based on these 2 weeks contents? If you have, you feel free to ask. Can anyone just summarize what all has been covered in lectures yet? Like I have seen the content, but I just wanted to know from your side.
I went through till week 1 content yet actually.
Okay, so
So till differential transformations I have seen.
mm-hmm.
What I am right now, the first week 9th question assignment.
uh,
I did.
so okay, so you are talking about the assignments that you have received, right?
Yeah. First week 9th question was a bit tricky.
Okay,
I
so
did not.
like we are not we are not allowed to solve the assignment questions as it is, but
Okay.
if you have doubt in some concepts, you can ask, like in that question. What was the question based on?
Uh, they're asking inverse of transformation matrix.
Okay.
If R is a rotation matrix and P is a column vector, which is a subset of.
Okay, so I think you might not have joined at that time. We solved a similar question
Yeah,
which was in previous year assignments also. So something like this, right?
yeah.
Yeah.
Similar to this.
So here, let me. Where was the file? I will show you the word file. Yeah. So yeah. So if, let's say, if this is a transformation matrix, the general form is that we have a we have a 3 cross 3 rotation matrix in it, right?
Okay, yeah.
This is a 3 cross
Yeah.
3 rotation matrix. This is a 3 cross 1 vector which denotes translation, right? And overall this is a
Hmm.
4 cross 4 matrix. So inverse of this is, like, we do the inverse of the rotation part, R inverse. Then what we do, basically we multiply the inverse of rotation matrix to the column vector and then take a minus sign. So this is the way you write the inverse of the transformation matrix, right? In this assignment's question, what it was asked, it was asked, like, I'm talking about previous year's assignment, so it was asked the inverse of the transpose of the transformation matrix. So we just did a transpose of this matrix, and since R inverse is its own transpose, so it becomes like this. So basically, like,
Yeah.
I will try to give you a sense of how this comes up, like minus R inverse P. So let's say this is a transformation matrix from frame A to frame B, right? So let's say we have a frame A and we have a frame B, right? And we are transforming by, we are doing some rotation, and we are also doing some translation. Like, this is what homogeneous transformation matrix do. They are just like
Yes.
putting those two things together, and we can directly in one single computation we can compute the new coordinates, basically, if you are transforming. So now let's say this transformation is given by T. Now if we are coming back from B to A, which is the purpose of T inverse, so let's look at these two parts separately, right? So first rotation part, you can just, like, if you rotated from A to B using R, then you can rotate from B to A using R inverse, right? So that part is straightforward, that okay, the transformation had rotation matrix R, then inverse transformation will have rotation matrix R inverse,
R inverse.
right?
Okay.
Now the slightly trickier part is what to do with this P, how to
Yeah.
invert this one. So now this P, if you imagine, so let's say P is a 3 cross 1 vector, uh, P1, P2, P3. So P1, P2, P3, right? So it would help to be little bit figurative. Let me draw some pictures here. So for now, let's assume that we are just translating and there is no rotation, right? So this is frame A and this is frame B, right? And we are just translating. So this is the initial origin, and this is the final origin. So the vector between these two, don't mind the curved line, like I couldn't draw it much straight.
Yeah.
Yeah. So basically this P1, P2, P3 is what this vector has that information that okay, shift these the A frame by
Yeah.
these three coordinates like P1, P2, P3. Now
Hmm.
let's say we are not rotating, we are just translating. So if we want to come back from B to A, we have to do minus P, right? Just move
Yes.
back by those quantities
Minus P.
P1, P2, P3, right? Okay. So that might give you the intuition of a minus sign. Now, where does the R inverse comes from? So remember, R is transforming from A to B, right? So B will, right? So R inverse will transform from B to A. Okay. So what we want to do is this R inverse P. This is what this is doing is that it is first transforming this column vector from from B frame to A frame basically, right? So the thing is that if in this case the B frame was not rotated, it was just translated, right? So the P vector remained the same even after we changed to, sorry, the P vector remained the same even after we transformed from A to B. But in the case where we are rotating also, so the P vector, the description of P vector won't be same in frame A and frame B, right? In frame A it would be different, in frame B it would be different, right? So to change the description of P vector, we are again coming back using R inverse, right? I think I lost you. Pramad, can you hear me?
Yeah.
Yeah. So what I'm saying is that think of it is that you are also transforming the translation vector. Like the coordinates of translation are not the same now because we have also rotated, right? So in order to find the inverse transformation, you have to describe the translation in other frame, right?
Okay.
So
Yeah.
that's
Got
why
it.
we are again multiplying the translation vector also with the rotation matrix and then subtracting it basically, like not in the sense subtracting it, but the idea that I gave you, that we have to do minus
Negative.
P, yeah, negative of that in order to come back. So yeah, like this might, you
Yeah.
can
Adding.
think of through this once again, on your own, and then it might take some time to get a feel of it. uh, yeah, it gets slightly confusing sometimes. uh, yeah, any other doubts?
Good evening, sir. Can you hear me?
Yeah, I can hear you.
Sir, it's with reference to lecture number 9. Lecture number 9. My doubt is, sir, Daba T by Daba Q2. In that derivation, at 13.48 minutes, it's told that for a prismatic pair, the matrix should be, there's a matrix given for that.
Mm-hmm.
And in that matrix, it's told that the value should be 0 in the second row and first column. Sir, do you have the reference of that lecture video
uh,
right now?
Not right now, let me just pull it quickly.
Yeah, sure, sir. I'll wait, no problem.
This is week, you're talking about week 2, right?
Week 2, manipulator Jacobian. There is a
Okay,
lecture.
manipulator Jacobian.
Yes, sir.
Mm-hmm.
Sir,
And
in that, if you could scroll to 13.48.
can you tell me, like, there's a PDF here, so it might be here also.
Yeah, okay, sir. It's slide number 6.
Slide number 6. Okay.
Yes,
Yeah.
sir.
This one.
Yeah. Sir, could you just glance through? It's given for prismatic joint. In that matrix, it's given the second row, first column. It's said as 1.
Yeah.
Yeah, and sir, in the lecture, it's corrected to 0.
Okay, so
sir,
in lecture it was said that this would be 0.
yes, and I have that right now on. Should I share it, or I have that shot of the lecture in which it's told it's 0, because sir, this plays a role in question number 6. If that matrix is as mentioned in this handout, if it's correct, then we'll get the answer. But if, as told by sir, if it is 0, then we don't have the options in that question.
Okay.
Yeah, that's. If the handout is correct, then no problem.
Yeah, let me just see if
Yeah.
I can figure it out right now, or else I will revert
Yeah.
back to you.
It's
So
in 13.48 in the video. Approximately, maybe 1 second here and there.
let me play this also.
Yes.
13.48.
Yeah, थोड़ा सा फर्क रहेगा सर इधर उधर.
हाँ.
So the derivative of this will become simply, here it is 0.
हाँ
So
सर.
we substitute in the, here it is 0, is nothing but
तो
derivative
अगर
of
सर वहाँ 0 पुट
this with
करते तो
respect to
ऑप्शंस
di.
अलग हो जाता है क्वेश्चन.
I get your point.
Yeah.
So let me just play from slightly back.
Is nothing but, so the derivative of only d matrix. Simple matrix multiplied by, so we can see that the derivative of I minus 1 ti is given by this matrix multiplied by the same I minus 1 ti matrix. Similarly, if it is a prismatic joint, then only di is the variable. The derivative of this with respect to di is nothing but, so the derivative of this will become simply, here it is 0. So
I think so. Here he's saying that we are differentiating with respect to di, right?
Yeah.
And if we see this matrix, right? So if we differentiate with respect to di,
Yeah.
then only one will come here only, right?
Yeah, that will come there.
Yeah.
Right. So if it's if the handout is correct, it's okay. But if we have to correct our answer according to this, then we don't have options in the answer. That's what is the problem. If handout is correct, then it's okay, no problem.
Okay. Because like what, going by the statement that the professor just made, I also think
this will become simply, here it is 0.
this will also be 0.
So
Yeah.
we substitute in the
Under that
dt.
circumstances,
You are not getting the right answer.
yeah, I will do it once again. But it will be better if you could check it from your end. I will do it once again.
Sure. I will take
Yeah.
a note of this. So
And sir, how will we come to know revised answer mode?
so we can discuss this in the next week's discussion hour.
Yeah, but the problem is, sir, it's given as 8th of February.
Okay, so the submission date is before that.
Yeah.
Right. So as of now, I'm not sure if there is any other way to communicate in
Yeah.
between.
Yeah, that's the problem.
Yeah. Okay, like I will try to figure something out.
Just
Maybe
check that options available according to this matrix. That also is okay.
oh, maybe you can, I guess there is a feature of forums and all also,
Yeah.
right? So maybe you can raise this query there and see if
Okay.
either the professor or other students might also chip in and just
Yeah, right.
help you there.
Because if we solve as per the handout,
Mm-hmm.
we are getting the answer.
Yeah, I got
And
your point.
it plays only for a fraction of second or so.
Mm-hmm.
Yeah, if someone misses it, he will get the answer according to handout, and
Yeah.
maybe that is wrong.
Yeah, I will see once again like assignment also, but
Yeah.
right now I cannot just confirm.
Yeah, it's okay, sir. No problem.
Yeah. Yeah, thanks for bringing this up. This might be an
Yeah.
issue for other students also who might have
Yeah,
missed.
right. Yeah. So can I ask one more doubt?
Yeah, sure, go ahead.
Time permits? Yeah. So when we find out alpha as the angle between zk and zk minus 1,
Mm-hmm.
so when is it positive and negative? Like it's a bit confusing. Yani positive कब लेते हैं? Pi by
Yeah.
4 positive and negative कब लेते हैं?
Yeah, so the definition, if you will see, is angle between zk minus 1 and zk about xk,
XK, yeah.
right? So it depends how have you defined xk. Like you let's say if the rotation is along the positive direction of xk, then you will take plus sign there, and if it's like in the negative direction of xk, then you will take a negative sign there. So while visualizing the angle, just note whether you are rotating in the positive sense or the negative sense.
So positive in the sense you would like to say it's anti-clockwise.
Yes, anti-clockwise. So right hand thumb rule, anti-clockwise, you will if it's rotating anti-clockwise, thumb is pointing along the positive direction of the xk, then it will be positive, and in the other case it will be negative.
Okay, fine. Just we had covered up till manipulator Jacobian with example.
Okay.
That was yeah. There is absolutely no problem in the lecture except this one which I had mentioned.
Hmm.
Apart from that, the contents are fine. Thank you.
Okay. Yeah. I think is there anything else from any side? Because I think I have covered everything what I have planned for.
Yes, it will help a lot in solving the assignment. Thank you.
Yeah, thanks, Joss. So I think we can wrap it up for today, and I will meet you guys
Yeah,
in the
Thank-
next week. Right?
thank you, sir.
Okay, guys. Bye.
Guys.